Okay, so for this enzyme kinetics, very important here is we need to understand the concept of the ES complex formations. Okay, from enzyme with a system with the enzyme with substrates, and at the end we will get back the enzyme plus the with the products. Okay, now always remember in this system means that in any reactions you will have the mixture of enzyme substrate complex, and together with the product. Okay, so means that here this enzyme, if I want to put it to write it more precisely, this enzyme must be a free enzyme. What's a free enzyme? Means the enzyme that haven't bound with any substrate. Are you clear? Okay, so always be careful about this EF. And the enzyme here, it must be the enzyme that without substrate. If the enzyme with the substrate will be this. Are you clear? Okay, and then we do know that for any rate of reaction, okay, we can actually use the delta or dp over dt. Now, what does mean dp over dt? Dp over dt basically mean how fast products can be formed. So it's measured by the number of mole of products formed per second. Okay, number of mole of product formed per second, and we do know that this, okay, how fast products can be formed totally depends on how fast I can form the ES complex. Correct or not? Okay, if I have high concentration ES complex, I can predict that I will going to have high products, form per unit times. So according to the rate reactions, this rate constant, so V naught also equal to K2ES. Okay, so we're going to use this K2ES now to derive Michaelis-Menten equations. So for today, we're going to look at this, how Michaelis-Menten equations can be derived, and why Michaelis-Menten constant, the Km, actually represents the affinity of the substrate, affinity of the enzyme for its substrate. Okay, so we're going to look at these two, and then we're going to look at this why. Okay, we always say that half Vmax, when half Vmax, we get the Km. Actually, this is a bit of wrong concept that we are going to look at it. What is the correct concept here? Okay, so first of all, let us look at this Michaelis-Menten equation and how we derive this Michaelis-Menten equation. Okay, so now let us start how to derive. Okay, so actually it's not really complex, but because this is mathematical, so a lot of mathematic concept we need to know first. Second, also we need to know, okay, a bit of enzymes property. So therefore, that means a little bit hard when you come to the final part here. So again, you have to understand that in a system with the enzyme and substrate, so my free enzyme EF, my free enzymes, okay, together with the substrate, we are going to get the ES complex. Clear now? And this ES complex can be broken down into the enzyme, free enzyme together with the product. Okay, so I label the equation. So this is equation reaction number 1. This is reaction number 2. The reverse one will be -1. Reverse one will be -2. Okay, until this part clear. Any system you have, enzymatic system, you have this. So this is general equation. Okay, general equation. Okay, so now if you look at this, we look at the reactions number 1. For reaction number 1, okay, so reactions number 1, what is the rate? The R here stand for the rate. Rate number 1 actually means that equation number 1, rate of this reaction number 1, proportional to the concentrations of the free enzymes and proportional to the substrate concentration. Correct or not? We always say that the rate will be affected by the enzyme concentration. So this is enzyme concentration affected by the substrate concentration. So substrate concentration, so proportional. So the higher the enzyme concentration, the higher the substrate concentration, the rate will be higher. Correct or not? Are you clear? So it means that in this rate will be control. R1, rate number 1, will equal to the rate constant 1 multiplied with the free enzyme concentration multiplied with the substrate concentration, according to the rate reactions, okay, rate of reaction. So let us look at reaction number 2. If you look at reaction number 2, So how fast I can form product actually depends on the how fast I have the ES complex or not. So rate of reactions for the equation number 2 actually proportional to the enzyme substrate complex equation. So the enzyme substrate concentration in this case. So it means that rate number 2 will equal to the rate constant 2 multiplied with the ES complex. Okay, clear? So different rate constants, okay, different rate constant. We have constant number 1, constant number 2, they are the multiplier. Okay, they are the multiplier. Okay, so if you're still not confused about this rate constant, I will show you again later. Now, equation -1. Equation -1 here is, okay, again, rate for -1 actually, not equal, but proportional. Okay, proportional to what? Against how fast I can break down ES complex to form back substrates, and also the free enzyme also depends on the ES concentrations. So therefore, rate -1 actually equal to K, rate constant for -1 multiplied with the ES complex. And last -2 reactions here, okay? So how fast, okay, I can form back this ES complex. So rate number -2 actually proportional to the enzyme, free enzyme, and also the product. So reaction number 2 equal to K -2 EF and P. So mathematics, right? We learn about this. Okay, in chemistry also learn about the rates. Okay, now until this part, okay or not? Very simple. Just let's, okay, clear? Okay, I haven't started anything yet. It's just to show you guys how to link. Okay. Now some students ask me why we need to have the K1 or K2 there. Okay. So now what's mean K1 and K2? K1 and K2, they are the rate constant. Okay, they are the rate constant. So what does rate constant mean? Now, for example, okay, let me show you. Okay, this is a bit mathematics. Okay, so let's say for example, we know that rate of reactions V naught proportional to the substrate concentration. We say that V naught, okay, proportional with the enzyme substrate concentration, for example. Okay, so if you look at this, if enzyme substrate concentration, this V naught. So if the enzyme substrate concentration equal to 2 units, V naught may be 10 units per second, for example. Okay, and then I increase to 4 units of the enzyme substrate concentration, I'm here may get 20 units. So in this case, we know that V naught proportional to the ES complex concentration, but it doesn't mean that V naught equal to ES complex concentration, cannot, because 2 cannot equal to 10. But we do know that V naught actually equal to a constant multiplied with the ES complex, okay, constant, for example, K2. So this constant actually equal to 5. Can you see that it's a multiplier, something like multiplier, okay? So we call this as a rate constant, okay? Understand? So come back to this. Okay, come back to this. So before we start to derive this formula, okay, I mean Michaelis-Menten equation. So first thing, according to the enzyme system, the very, very important idea here is the rate of formation of ES complex equal to the rate of breakdown of the ES complex. Okay, so first, the rate of ES formation will equal to the rate of ES complex breakdown. Okay, understand or not? Now, which one actually ES formation? So I use a red color to circle. This is the formation of ES complex. This is the reactions that form ES complex. Cannot. Can you see that? So the equation number 1, we form ES complex. Equation -2 also form ES complex. I use green color. This one actually is a breakdown of ES complex. That's why we form products. This one actually is a breakdown of the ES complex from the substrates. Can you see that? So means that if you want to put it here, we total up. So the rate that formation will be number 1 and -1. So rate for -1 as number 1 plus rate for -2 will equal to the rate for -1 plus rate 2. Can you see that? Because rate 2 and rate -1 is the one that break down the ES complex. Rate 1 and rate -2 is the breakdown of the ES is the formation of ES complex. Correct? Number 1, number -2 form ES complex. This one break down ES complex. Okay. Now, because our focus is initial rate of reaction. So initial rate of reaction means that the time almost equal to 0, where the product's concentration actually approaching 0. Am I right? Initial rate of reaction, when the time equal to 0, when the time very, very near to 0, reaction just started, the product's concentration almost equal to 0. So if the product also equal to 0, so means R -2 will approaching 0. So means that almost equal to 0, so can be neglected. Okay, can be neglected. Are you clear? We can ignore the effect of this. Correct or not? Are you clear? Because when T almost near to 0 means that my product's concentration also almost near to 0. So therefore the rates almost equal to 0. Okay, something like you don't have substrate. How are you going to form ES complex? Correct or not? Okay, the concept. So therefore in this case I say that R -2 equal to 0. So therefore now you can see that R1 equal to R -1 plus R -2. So this is the first step that we are going to start. Okay, R -1 plus R -2. So what is mean R1? So R1, look at this, is equal to K1 EFS. Okay, R1 equal to K1, substitute, EF, substrate concentration, R -1, can you see that here? K -1 ES. R2 equal to K2 ES. Are you clear? Okay. So now what we're going to do here is, look at this. I simplify it. I didn't do anything here, but I simplified here by taking out, factorize the K -1 plus K2 together. So left with ES complex. Okay, left with ES complex here. Okay, then I leave the EF here and substrate concentrations. So this one will equal to K -1 plus K2. I take all the rate constant, put them together, multiply with the ES complex. Okay, I multiply with ES complex. So Michaelis-Menten say that this constant K -1 plus K2 divided by K1, this one is equal to the Michaelis-Menten constant. So this one actually equal to Km. Are you clear? Because lazy to write it every time K -1 plus K2 or K1. So we simplify it, represent it by Km. So Km actually is a rate constant. Okay, it's a what we call this? It's a ratio. Okay, so what is this ratio? I will tell you guys later. Okay, now but the question here is, I have the main question. In enzymatic reactions, even though time equal to 0, do you know how many free enzyme we have? Because immediately you add the enzyme in, some enzyme already bind with the substrate already. Correct or not? Some enzyme already bind with the substrate already. So means that we do not know what is the concentration of the free enzyme. But we do know that in any enzymatic system, we do know that total enzyme will equal, concentration of total enzyme will equal to the concentrations of the free enzyme together with the concentrations of the ES complex. So means that how many enzyme I have, actually some of them they still remain as a free enzyme, some of them already become the ES complex. So means that if I modify the equations here, so free enzyme will equal to the total enzyme concentration minus out the concentrations of the ES complex. So now I substitute this. Can you see that? I substitute this here. Okay, I substitute this inside, so I will get what? ET minus enzyme substrate concentration multiply with what? Multiply with substrate concentrations, then equal to the Km ES. Okay, clear until this part? I substitute only, I didn't do anything. Okay, I substitute, then I start to multiply it. Okay, expand it. So I will get what? Here I will get the E total enzyme multiplied with the substrate concentration minus ES complex substrate concentration equal to Km. Right, okay, I make it this way, and I bring this all enzyme substrate concentration, I bring it to one side. So means that cannot equal to Km ES complex, okay, plus ES complex multiplied with the substrates. So it's mathematics. Are you clear so far? I just do the mathematics part only. Okay, play around with this. So ET. Can you see that? So equal to what? Equal to, now I factorize, I get Km plus substrate concentration multiplied with the ES complex. So it means that if I leave it ES complex now, then I will get the divided Km plus substrate concentrations. Okay, until this part. Okay, so I stop recording a while. So now we know that's the Km plus substrate concentration already, substrate concentration ready. So now we have ES and ET, how we actually going to make them into the rate of reactions. Okay, so now try to imagine, what is the definition of rate of reaction? Definition of rate of reactions that we know that it actually is how fast product can be formed over time. And this, how fast products can be formed over time, if we go back to our equations, chemical equations here, okay, how fast products can be formed actually depends on the enzyme substrate concentration, cannot. So means that actually this one is the one that determine my rate of reactions, cannot. R2 basically means that my initial rate of reaction. If the R2 is my initial rate of reaction, then I can put K2 ES inside here. Okay. So V naught now also equal to K2 multiplied with the ES complex. Okay. So this is the first thing I need to know. Okay. Now, second thing, we do know that when Vmax take place, when Vmax take place means that substrate concentration no longer, okay, no longer act as limiting factor. Cannot. Okay, Vmax happen when substrate concentration no longer act as limiting factor. So what does this mean? So it means that we have a lot of substrate compared to my enzyme. Cannot. Okay, when Vmax take place, basically means that my substrate concentration is so high until, okay, my enzyme work at the maximum rate. So under this condition, when we say substrate no longer act as limiting factor, basically means that all enzyme active site are occupied by substrate. Correct or not? True or not? So means that, and I understand the concept here. So means that now you look at this, my total enzyme now actually equal the concentration of total enzyme, because all active site occupied by the substrate. So means that all enzyme now already form ES complex. Correct or not? Understand the concept? Because we see that when Vmax take place, substrate concentration no longer act as limiting factor. So when the substrate concentration no longer act as limiting factor, means that all enzyme now are bound with the substrate. So it means that if I have 100 molecule of the total enzyme, I know that now 100 molecule become ES complex. Are you clear? Okay, so now look at this. So any rate of reaction equal to K2 multiplied with the substrate concentrations. Correct or not? Okay, so when Vmax take place, so my all ES complex actually also equal to my enzyme, total enzyme, correct or not? Right? This thing, okay, two, this is general. Generally, okay, the rate of reactions depends on the how fast ES complex can be formed, and this is specific. Why is it specific? Because I want the particular rate of reaction, which is the maximum rate of reactions. Okay, so what we're going to do here is go back to this equation. Okay, so I multiply this equation, I multiply with K2. So if I multiply with K2, what we're going to have? K2 ES complex. Yeah. I'll tell you why I multiply K2. Then K2 ET plus substrate concentrations divided by Km plus substrate concentration. Okay, so now look at this. K2ES, so it's the V naught. K2ET, so it's Vmax. So V naught now equal to Vmax. Why we multiply K2? So that we can change it to V naught and Vmax divided by Km plus substrate concentration. So this is how the derivations of the Michaelis-Menten equations. Okay, so why Km value? Km value actually means that the substrate concentration that allowed, okay, the reactions, allowed the reactions to achieve half Vmax. So I'm going to explain this one. Okay, and also Km actually indicates the affinity of enzyme for its substrate. Cannot. And we do know that when the Km value is high, affinity is low. Cannot. Okay, so these are the things that we have learned previously, right? Okay, again, so few things that we have learned. So now we actually revise it back. Okay, so Km actually is substrate concentration that allowed the reaction to achieve half Vmax. This one, no, right? Okay, it's also indicates the affinity of the enzyme for its substrate. This one we know, right? And we do know that Km value is high, affinity is low, or vice versa. Km value is low, affinity is high. So this one we know. Okay, are you clear? So now we look at this, how we can actually explain, okay, this Km, why Km is the substrate concentration that allowed the reaction to achieve half Vmax. Okay, it's a substrate concentration. So now look at this equation again. V naught equal to Vmax substrate concentration divided by Km plus substrate concentrations. Correct or not? True or not? Okay. So wait now. Okay. So this substrate concentration, when you say that Km is a substrate concentration. Let's say, okay, if my substrate concentration equal to 1 unit, we substitute. So we get the V naught equal to something, but this something may not be the maximum rate, may not be half of the Vmax, correct or not? So I continue, I change. My substrate concentration equal to 2, substrate concentration equal to 3. So every time I substitute equation, I will get V naught, different V naught, correct or not? Okay, because when the substrate concentration increase, my V naught also increase, correct or not? Okay, but if let's say, so happen that my substrate concentration now equal to the Km. What is the Km? Km is substrate concentration, right? If I increase number 1, 2, 3%, 4%. If let's say Km equal to 5, so I increase until 5, what will happen? Means that my substrate concentration now equal to Km, correct or not? So means that my substrate concentration now become Km, substrate concentration become Km. So means that my V naught now, my rate of reaction equal to Vmax multiplied with Km over Km plus Km to Km. So Km and Km can cancel. So can you see that when the substrate concentration is Km, they allowed the rate of reaction to reach half Vmax. Can you see that? My substrate concentration is ngam equal to Km, not 1, not 2, not 3, not 4, not 10, but ngam Km, exactly Km. Then you can see that substrate concentration equal to Km. Then I can actually remove this Km because we multiply, right? So we go the half Vmax. So that's why we always say that Km, why half Vmax? Why not 1/3 of Vmax? Why not 1/10 of Vmax? Why not 2/4 of Vmax? But why always get half of the Vmax? Because when you look at this Michaelis-Menten equation, this is how we get half Vmax. Are you clear? Okay, so very, very simple what call this demo why Km actually is a substrate concentration that allowed the reaction to achieve half Vmax. Okay, so the first part I have done. Okay, so we're going to look at the second part here. Affinity or enzyme for a substrate actually indicated by Km. Correct or not? So look at this. If affinity is high, okay, so if affinity is high, basically means what? Basically means that enzyme will always want to bind with the substrate to form ES complex. Understand this concept first. Affinity. Okay, if you like something, you want to be together, right? If you like your handbag, you always want the handbag, you always want to carry the handbag out, right? So it means that affinity is high, basically means that you want to form more ES complex. Okay, then look at this equation now. If you look at this equation, rate constant for K-1 is the breakdown of ES complex kernel. Okay. K2 also break down ES complex kernel. Okay. K1 is the one that form ES complex kernel. The rate equations, right? Okay, I string it now. You look at this. Okay. Already my pointer. Now look at this. Here's my pointer. Okay, can you see that? K-1. K-1 here is the rate constant for form A. K-1 is the for one that break down ES. Don't want ES. Don't want to form ES. Can you see that? K2. K2 also don't want ES because break down ES. Okay. K1. K1 is the one that want form ES complex, cannot. So means that the top part here is for the breakdown of the ES complex. Bottom part here, okay, the denominator here want to form ES complex. Okay, so now let us look at this. What is this made? Now, if affinity is high, when affinity is high means that we want to form ES complex more. Can you see that? So means that the rate constant here increase. K1 increase very, very high because we want to form ES complex, cannot. If you want to form ES complex very, very high, what is Km value? Km value lower. So this explains why Km value lower, affinity is high, because we want to form ES complex. So now explain to you guys, some of you guys actually did ask me why Km value is low, affinity is high. So now I can explain by this, correct or not? Because I want to form more ES complex, so means that K1 must be high value. When K1 is high value, therefore Km will be lower. So therefore Km lower, affinity is high. Clear? Okay. But if let's say affinity is low, affinity is low basically means what? I don't want to form ES complex so much. Okay, I don't want to form ES complex so much. So means that ES complex lower. So means that Km higher. So that is why we do know that when Km value is high, affinity is low, because now less or fewer ES complex can be formed. Are you clear? When affinity is lower, we have less ES complex to be formed. Therefore, Km value will be higher. Okay. So with this, I have done for the first part here already. Okay. So the whole enzyme kinetics that we need to know actually Michaelis-Menten. Okay, let me do a summary here. What you guys need to know after this. Okay, not the derivations of the Michaelis-Menten equation. So what you need to know first, what is the Michaelis-Menten equation? Michaelis-Menten equation actually try to link or relate V naught, Vmax, okay, substrate concentrations, and okay, Km together. Okay, V naught, Vmax, substrate concentration, and Km together. So that in these equations, V naught, do you need to memorize? The answer, no need. V naught equal to Vmax substrate concentration divided by Km plus substrate concentration. So once I have this value, Vmax value and Km value substituted, then I can actually put in any substrate concentration to get the V naught. Are you clear? Once I have Vmax, once I have Km, I can always put in substrate concentration to get the V naught value, or I can put in V naught value to get what is the substrate concentration I need. Okay, so how to get Vmax? Always say that you can get from the V naught versus substrate concentration curve. This is where we get the Vmax. And from the Vmax, we halve the Vmax. Then I will be able to get the Km. So it means that this Vmax value, Km value, I can substitute here. Therefore, I can have the equations. Okay, that's one. Second, so we need to know what is Vmax. Vmax occurs when substrate concentrations no longer act as limiting factor. So means what? Means that substrate concentration is of more substrate compared to the enzyme. So means that at particular times now we know that enzyme active sites, okay, are fully occupied by substrate. So means that my enzyme work at the maximum already. You cannot further increase. That is the maximum already. Are you clear? Okay, so there is a Vmax. And in this case, we know that's the Km. So what is the Km? Km actually equal to the substrate concentration that allowed the reactions to achieve half Vmax. So I already explained why they will get half Vmax in the just now, the lesson just now. So it's also its indicator. Indicate what? It indicates the affinity. Affinity of what? Affinity of enzyme for its substrate. So it means that we want to form the ES complex. Correct not? Okay. So in this case, how we interpret the value when the Km value is high means that affinity is low. Are you clear? And vice versa, when Km value is low means affinity is high. And I also show you guys how actually this related to the formation of ES complex as well as the breakdown of the ES complex, okay, to show you guys the affinity, okay? So these are the things that you guys need to know, okay? A summary. Okay,